this will be the last seminar before the break of the summer, and we had the talk of Dennis Kent last time, which was about magnetic reversal, and we have one thing that is extremely important as well is the possibility to make absolute timing. And this is done with, for all time, it's done mainly with uranium lead. Uranium lead measurement is crucial. And what is important is to know what is the accuracy of these measurements. So we are very happy to have Urs Schaltegger from University of Geneva, who is the state-of-the-art laboratory for uranium lead measurement. And so I hope we will have, you will transmit all your knowledge in 1 hour. You have to show us all your know-how, so we could be inspired and also understand what are the limits and the possibility of this technique.
Thank you very much. It's a big pleasure to give this lecture. I really hope for the Americans that they will not fall asleep. It's indeed a lot of material for 1 hour, because I have somehow to make the bridge between sedimentary deposition, dating of some ash beds in between, and then the mineral zircon we are using for dating, and the analysis, the analytical part of the whole. And Jacques was asking me really to cover from the basics a bit, the techniques a bit, to the applications. That it's I really try to offer a crash course in 1 hour, which of course is will fail in any case, but I do my best. Huh? So this is a bit kind of what I would like to speak about. I will very quickly give a bit of the physical background, and also of the history, how these methods have developed. And then we will speak mainly about one technique. And this is what we call in our slang CAID TIMS, so chemical aberration, isotope dilution, thermal ionization, mass spectrometry. This is the technique which gives us the highest precision, highest accuracy age information. And I will show you what is the workflow, how we measure uranium and lead isotopes, what actually is influencing our precision and accuracy, what is critical for this. And a very important central point in all this is something very physical of our material, is the radioactive decay damage of zircon. So we have to spend a little bit of time understanding what this means and how we try to get around this problem. It's a major problem. So we will speak about chemical aberration. And then we have to speak about how we interpret zircon dates. I started my career in orogenic processes, granites, geochemistry, and was using zircon dating in this context. And somehow with the many years I slipped over to the sedimentary world. But we have the same understanding we need to have when we date zircons in magmatic rocks or in volcanic rocks. We also have to have when we date ash beds in sedimentary successions. So we have to be able to understand and how to interpret these age patterns. So then I will speak a bit about this aspect. How do we quantify time in the sedimentary records? So how do we calibrate time series, compare time series, establish age models, and then also show some application that will stick to one specific application. That's the Permo-Triassic boundary and the Siberian traps as large igneous province. So to exploring a bit this large igneous province climate relationship via geochronology. What are the limits of establishing this link? So this is really basics. Huh? So we know that radioactive isotopes like 238 uranium, they decay to radiogenic isotopes like 206 lead. So 238 uranium is here. Everything which is green is this decay to 206 lead. But of course, these are 32 masses mass difference, so this cannot be one decay, this doesn't exist. So this is a series of 8 alpha decays. And then the same is valid for 235 uranium, so this decays via 7 alpha decays to 207 lead, and the 232 thorium decays via 6 alpha decays to 208 lead. But now, so we are only interested in the parents and in the daughters. All the rest in between we ignore because we are dealing with old rocks, and we call this is a so-called insecular equilibrium. So daughters become parents again, decay, etc. So all this is going on without notice. We only consider the ultimate parent, the ultimate daughter. And in this chart of nuclide, so we have atomic number on this axis and the neutron number on this axis. We see that the alpha decays, they go in this direction here. And so they always lose 4 masses difference. And beta decays are isobaric, so they go this way. Then we have to know what is the duration of our radioactive decay. Well, we have to understand what is the half-life. So when we look at the 235 uranium, in the beginning of the solar system, we had a certain amount of 235 uranium, so 100%. And then it takes some time until half of this parent is decayed into the daughter. And this is called the half-life. So in the case of 235 uranium, this is only 700 million years. So after 1 half-life, we are here, 2 half-lives, 3, 4, 5, 6 half-lives. We are here somewhere now with our solar system age, and we see that very hopefully there is not too much 235 uranium left on this planet and in the solar system. So most of it has decayed, and so the system is close to be extinct. Whereas the 238 uranium has a much longer half-life, so we are actually today about at 1 half-life. So about half of the 238 uranium has decayed, and the other half is still available because the half-life is 4.47 billion years. So the age of the solar system is something like 4.57 billion years. And then the thorium has a much larger half-life, so we have only started with this. It will be, so we will reach 1 half-life in several billion years only, so this is decaying very, very slowly. And now there are two aspects to this. So first of all, from now on, we ignore completely the thorium-lead decay system. This is mainly because of analytical limitations, because when we want to do thorium-lead dating, we would need a hot lab, so a lab which is capable of handling very radioactive materials, which geochronologists usually do not have. So we only consider the 2 uranium-lead decays. And the other one is that the half-life is defined via this equation here, or linked via this equation here to the decay constant. So we know the decay constants from some old papers, 1970, 1971, and we still use them even without having a really analytical uncertainty attached to these values we are using. And at the very moment, the new determinations of these decay constant is underway in the United States in the labs of the Jet Propulsion Lab and in Los Alamos. So hoping that at some point, we could rely on maybe a better determined decay constants. Okay, so we know the decay constant lambda from physical experiments. We take them as they are. We don't question their accuracy and the uncertainties which are attached to them. So we need to measure the concentrations of our parent isotopes and our daughter isotopes, and also the exact uranium-lead ratios in our sample. We need a mass spectrometry to analyze the isotopic composition of uranium and lead. So a mass spectrometer can only measure an isotopic ratio. So when we want to go to concentrations, we need to have an isotope dilution technique. So we add a tracer solution, artificial tracer solution from outside, which we know exactly the uranium-lead ratio and the concentration. Then we also can calculate concentrations. And when we have all this, we can calculate an age. Sounds very simple. But so we can do all these analysis and we calculate an age. So now you may know that there are also different techniques to do this. So there is an analytical equipment which is called SIMS, secondary ion microprobe, or MS, mass spectrometry, secondary ion mass spectrometer. So this is called an ion probe also, which is analyzing very, very small volume of zircon. So you can, a small pit of 10 to 13 microns, you can give an age. You analyze very little material. Then there is another method, which is called laser ablation Icpms, inductively coupled plasma mass spectrometry. So you make your primary beam is a laser in this case is an ion beam. You make big holes, you analyze quite a large volume, goes very fast. So these are two spatially resolving methods, but they're both low accuracy and low precision. Here because we analyze very little, here because just the whole setup is very simple. This is not done with equipment which is capable of providing precision. And what we do is Icpms, isotope dilution thermal ionization mass spectrometry. So we can handle small zircons as small as this. So actually the volume we analyze can be smaller than with a laser ablation pit. And but this is a bulk, so it's very precise, very accurate, but it's a bulk technique. So we analyze a whole grain with all its sequential growth zones in this grain, and we do not have this spatial resolution we do have with these two methods. So from now on, we will concentrate only on this, because only this method can provide us with the necessary precision we need to resolve the time in sedimentary successions. And then I make a small bracket. Of course, we need a long series of technical developments to be able to do this. We had to learn about radioactivity. We had to develop mass spectrometry. We needed all the nuclear research of the Manhattan Project to get to the point that we can analyze isotope ratios. We needed the production of these tracer isotopes for isotope dilution. We needed the discovery of Teflon, simple as this, catalyzers that we are able to actually measure smallest amounts of lead. We needed to develop distillation techniques that allow us to produce the most clean acids ever. We needed to develop this exchange chemistry to separate the uranium and lead from trace elements, and so on. We also needed to develop techniques that we can remove the surfaces or other parts of grains. We will come back to this. And also other technical developments. Of course, in the same time frame was also the development of the spot dating techniques. That's more the technical side. And then we needed a lot of conceptual development. So somebody came up with this diagram. It's called the Concordia Diagram or Weatherill Diagram. So this is 206 to 38 uranium ratio or age here, and this is the 207 lead to 35 uranium ratio or age, and this is the Concordia. So any point which gives exactly the same age for these two decay systems will be on this curve, because this one has a much faster decay constant than this. This is not a straight line, this is the curve, hopefully. So we had to understand the relationships when the points are on this curve and the points are not on this curve, so then they are called discordant. We had to understand, first of all, was understanding of lead diffusion in the Zircon lattice. This was very much linked, soon was linked to radioactive waste disposal. Not yet in 1960, but soon later it started. We had to learn about what is the radioactive decay damage doing to the Zircon lattice, or the decay is doing to the Zircon lattice. We also found out that zircons do not just represent one age, they grow. from here to here. So this can last maybe 10,000 years only, or can last 500,000 years. Or then there are parts of the grain which are much, much older. So this part of the grain could be 3 billion years old, and this part of the grain here could be 200 million years old, for instance, or 1,000 million years old. So this is called inheritance. So these were all conceptual developments, mostly in the 60s. And then there was a long, long, long period of developing these concepts until quite recently, where we started to realize that actually, of course, it's logic, it's trivial. Zircon grows over time. So we have between the growth of this nucleus and the growth of the last zone here, there is time. But we at some point we managed to get so precise that we were also starting to see this time. And then there is a completely different issue, is that the people started to quantify time in the evolution of Earth. So this is not the first geological timescale, but it's a nice one. Arthur Holmes, 1959, where he put the depth of a sedimentary basin in feet versus millions of years. So he was putting the Precambrian-Cambrian boundary to 600 million years. Nowadays, we think it's 538.7. This is the Permo-Triassic boundary, which he put to 225. Now we know it's around 251.9. And the Cretaceous Paleogene boundary, which he put to 70, is now 66.02. So actually, it's quite accurate. And so time is somehow close, quasi-linear in. So sedimentation in this example here seems to be quite linear in time. Okay, and then there is one thing which is maybe counterintuitive. So this is a diagram which is from this paper by Blair Shaney in the Treatise of Geochemistry, very simply showing the sample weight we are using for dating. So 1970 something. We have used milligrams, many milligrams of zircon to be able to analyze them and to put a date on an analysis. Nowadays, we are here, actually, 1-2 micrograms is standard. So we are dealing with very small zircons or fragments of zircons. And counterintuitively, during this decrease in sample volume, we have an increase in precision. So our precision level decreased from 1 to 2%. Now, the best we can do is better than a per mil on a 206 lead 238 uranium date. So this is a lot of method development which was done over these many years that we are capable of today to get there. And we will explore later a bit in my talk why actually we need to decrease sample material. It's essential for understanding the systematics of the isotope system in the minerals we date. Okay, so I said before that the method of choice is the bulk method, the chemical aberration, isotope dilution, thermal ionization, mass spectrometry. Why? Mainly because of its precision. Because when we have one of these two spatially resolved techniques, we are speaking about a few percent of single spot uncertainty. And when we have a series of spots which give the same age, we can hope to get a weighted mean age which has an uncertainty of around 1%. When we do CAI TIMS, we have on a single crystal an uncertainty of maybe 2 per mil to 0.5 per mil. And when we have when we manage to have a series of grains at the same value, at the same date, we can hope to have a weighted mean age of something like 0.2 per mil. So we are getting significantly more precise. So what is this now, this CAI TIMS? So we have to get our zircons out of the rock, so we can crush the rock, separate them, or we can also make thick sections of slabs of this rock, go in an imaging device like a chem scan, see where the zircons are sitting, extract them. But finally, they have to go somehow in epoxy resin, get polished down to half, and then we can do imaging and also so CL imaging, cathodoluminescence imaging, and we can also do in situ analysis of trace elements of hafnium isotopes, oxygen isotopes by using laser ablation, Icpms, or an ion probe. But then ultimately we decide that we want to analyze this zircon. We take it, we pluck it out of our epoxy mount, we do our chemical aberration, we add our tracer, put them in an oven under pressure and dissolve this zircon. Separate uranium and lead, and then so we can analyze the isotope compositions of uranium and lead, and via the tracer composition, we can calculate the nature and the concentrations. And we also have the possibility, what we have separated here as a trace element fraction, we can do trace element ratios at least from this solution, or hafnium isotopes from this solution. But this is called Zircon petrochronology, which is kind of a half intelligent name for this. Important is to know in this whole context, in this whole procedure, where are actually the critical points, the critical moments. So what influences most the precision? So we are using a software which can make from each analysis these fantastic error cakes, which are really a very good way of showing what are the sources of error in our analysis. So analytical precision, so the analytical uncertainty from our uranium and lead measurement, and also the mass fractionation, that's one part. And analytical precision has to be largely improved over the last years. So what we improved is the signal to noise ratio in our equipment. And we have developed more stable electron or photon multipliers. We use them now in digital mode as ion counters. Since many years, we discuss about high resistance amplifiers that are linked to Faraday cups. So when I was a student, we were only measuring on 10 to 11 ohm resistance Faraday cups. Now we have either 10 to 12 or 10 to 13 ohm. And now there's a new generation of capacitive transimpedance amplifiers, which have other systematics or characteristics that do not follow these normal systematics of the high resistance amplifiers. So there's a lot of technical development which has been done. And then the control on mass fractionation. So when we measure an isotope ratio on a mass spec, we are sure the mass spec is measuring wrong. Each mass spec has its own way of measuring a certain isotope ratio, and this is called source fractionation or fractionation in the analysis. And we have to overcome this by producing these tracer solutions. We add to our sample. It's not only for calculating the concentrations, but also because there's a double lead isotope, two lead isotopes are in there and two uranium isotopes. We know very, very well the isotope ratio of our spike or tracer, so we can actually correct online during the measurement our mass fractionation. So this was a major development, the formation of this Earth-Time International Earth-Time Consortium in 2004, and the decision that we produce our Earth-Time tracer solution. So maybe this is the holy mother solution here. You may be able to read here ET2535, so that's a 202, 205, 233, 235 spike. And this is the 535 without 2. This is one very, very important aspect of the developing the techniques. And then the blank. So this is when isotope geochemists or geochronologists are sitting together. They speak most of the time about blanks. So this is in a very clean lab. We want to minimize the amount of lead we introduce into the analysis via contact with materials and acids, also our hair, whatever. So we have now in Geneva, and also this is the same in other labs, Princeton University, MIT, ETH Zurich, we have total procedural blanks of something like 100 femtograms. So this is 0.1 times 10 to the minus 12 grams. And this is probably one of these limits we will hardly be able to go beyond as long as we do our manipulations by hand. And this blank is very important because all depends on this ratio here. This is the radiogenic lead, or the one which is produced by the decay of the radioactive parent. This is the common lead. So usually there's no common lead in the zircon, so it's all us, this our contribution. When this is as low as here, you see that the error of the analysis is dominated. It is mostly due to this contamination. When this is 15 or 20, then this part of the cake gets very, very small. So we have to be with this ratio here above, ideally above 20. And this we can achieve when we have very, very low blanks. And then there was one moment where we had to decide that we have to abandon the 235 versus 235 uranium to 207 lead decay. Why? So when you now go in the literature and you see our dates we are publishing, these are only 206 to 38 dates. And why is this? So we can do an analysis in green here. This is measured, state of the art, and is corrected for the procedural blank via 206, 204, 74, 84 ratios we have established during repeated analysis of our blank. But this blank is not every day the same. The isotope composition of this blank is varying, probably with the mood, with the COVID, with whether there's sun outside or not, nobody knows. Definitely with the person. So these are not values which are in stone. They have an uncertainty also. And when you move this value around, especially the 207, 204 value, when you move this value around within this uncertainty, you can move this ellipse far to the right, discordant, far to the left, inversely discordant. So actually the 207 lead to 35 uranium date gets insignificant and is depending only on the isotope composition of our common lead correction. So we forget about this. We only deal from now on with 206 lead to 38 uranium dates. So that's all very important developments, but the real challenge is still, since Tilton 1960 to today, is understanding what is happening during the decay damage to the zircon lattice and how this is relating to the loss of radiogenic lead out of the zircon lattice. So this is our uranium-238, which decays into 235 thorium. That's the first daughter. So this is an alpha decay. So it ejects an alpha particle, which is a helium-4, so 2 neutrons, 2 protons. Is traveling quite far, but because it's so small, it doesn't really manage to make a lot of damage in the lattice. But then there's also energy liberated, and this energy is pushing back the daughter isotope. This is called recoil. It's traveling a very short distance, but because it's big, it's making a lot of defect in the zircon lattice. So we can have a zircon lattice which has no damage, is fully ordered, 0% damage, or we can have a zircon lattice which is fully disordered, fully amorphous, so 100% damage. And so there were people in studying this, this was already a research which was done in the framework of developing possibly materials for radioactive waste disposal. So they defined what they call the first percolation point. So this is the first transition from a fully ordered to a partly disordered material. But here, the damaged areas are isolated. So isolated damaged areas where actually the lead here is mobile, is not anymore holding a structure, but it cannot leave because around is a fully ordered structure. And then they defined a second percolation point where these damaged areas start to link. And now when we have a lead isotope here, then it's also open to exchange with fluid phases. This goes out. This can now leave our zircon. So when radiogenic lead can leave our zircon, our age gets wrong, gets too young. So these two thresholds, they are equivalent to something like 30% amorphous fraction and 90% amorphous fraction. So reliably, we can only date zircons which are here. All this we have to forget. That's so this amorphous fraction in percent or proportion, and this is the radiation dose. So this is calculated with this equation. So it's the number of decays from 238 uranium to 235 uranium or 232 uranium. Sorry. So what now we have to do, because we always find such areas in our zircons, how can we now solve this problem? How can we get rid of such domains in our zircon? So that's the chemical aberration. So chemical aberration is a two-step treatment before we analyze the zircon. So we first thermally anneal our zircons 2 days at 900 degrees. So this is annealing of those parts who are at the first percolation point. So we just repair and restabilize the lead in here. And then after this annealing step, we put them at pressure in the same acids we use for this solution, 12 hours at 210 degrees. That's to remove all these areas which were at the second percolation point. So this is a good example, a non-treated zircon, and then possibly not the same zircon, but a zircon of the same population after chemical aberration. So we have removed quite a bit of volume, and we now can hope that what is left here is a zircon material with a completely intact lattice, so a closed system lattice. And Jim Mattinson demonstrated this with this. So 2005, he really invented this technique with the stepwise leaching. So first, all these zones which have high uranium, they get dissolved first. They have much too low H's, and then from step 3 on, maybe you get coherent H for the rest of the zircons. So with the low uranium concentrations. So that works in most cases, but it's purely empirical. And we would like to be able, of course, to quantify this. So this was an attempt. This was a student in my group who did a PhD, and part of his PhD project was the question: can we calibrate the conditions of our chemical aberration, or to tailor our chemical aberration in a way that it's optimal? So for this, we can use a technique which is called micro-Raman spectroscopy. So as a pristine zircon without decay damage would be in this diagram. Here there are two parameters which are coming from such an analysis. This is the Raman shift, or the Raman wave number. So a pristine zircon would be at 1008. And this is the peak. This is this peak at 1008. This has a certain shape. This is the full width at half maximum. So for a pristine zircon, this is a very sharp high peak. And then when it gets damaged, the peak gets lower and wider and wider. So that's what we see when we analyze now a series of zircons which are more damaged. They follow what is here indicated by the radiation damage trend. So they go this way here. And what we do now, we anneal them and then dissolve away what is really damaged. So we should find the conditions where we get as close as possible to pristine zircon. But that's about the best we can do. And we could kind of, Philipp Wiedmann, he could kind of quantify the highest, how to say, the highest confidence area where we are the closest to this pristine point, and that's 210 degrees, 12 hours. That's what we are using now for the partial dissolution step of our chemical aberration. And I would say this works in 95, 98% of the cases. This works very well. And cannot really be tested. We just have to hope that we are doing fine. Okay, so this was now the methods. And now something about the interpretation. So zircon is a magmatic mineral, so it crystallizes in a melt. And so we have to understand about how zircon is crystallizing in this melt, where it crystallizes at different levels, over how much time. This leads to very complex zirconate spectra, and we have to understand them before we can interpret them, the zircons, when they are deposited here. So this is a diagram melt fraction, so magmatic melt, 100%, 0%, from 600 to 1300 degrees. So the melt starts to crystallize several minerals, maybe also loses melt portions. And at some point, at something like 30% of melt fraction, we arrive at 68% of SiO2, and we enter this field, which is called the Zircon crystallization interval. So here, the melt is saturated for zircon. So most of the zircons will form here. Some of them will maybe form here in small patches, which are isolated and saturate earlier, but most of the zircons will form here. So that means the zircons will yield a range of ages. And also these volumes which are crystallizing are not non-monotonous, because we lose melt, volcanic eruptions, but then we also have incoming hot melt, which is recharging the magma system, is increasing the temperature, crystallizing again, increasing the temperature, crystallizing again. So our zircon age distributions will be definitely non-normal and will also very likely be multi-peak. So we have to be aware of this, because we also will find this in our ash beds. So we may find this in one single zircon. So you see here a first generation of growth, a second generation of growth, a third. So this could be inherited core, but it's not. So all this happens within 100,000 years maybe. And we can also hope that when we analyze 4 grains, we may find maybe a grain which is enriching the first growth phase, another zircon which is enriching the second. So mostly grew during the second or during the third, or maybe the fourth could be this very thin rim here. So we end up with age distribution, something like this Fish Canyon tuff, huge magma system, several different samples, they show zircon growth over 450,000 years. And via a lot of trace element modeling of fractional crystallization, of trace element partitioning, Jörn Watzlaw, he arrived at this model that this magma chamber was at 45% of crystals, then got nearly solid, nearly up to 80% crystals, but then was some hot magma incoming, remelting, reducing the crystallinity down to 45%, and then the whole system exploded. So Fish Canyon tuffs, 28 million years, it's one of the biggest volcanic eruption in the US, and produced something like 5,000 cubic kilometers of erupted ash volume. So all this happens. We are crystallizing zircons at different levels in the crustal column in an interconnected magmatic system. We are recycling them. They grow over time. We have incoming basaltic magma, which is remelting, recycling zircons. They are introduced in new magma batches. Some of these magmas are stored crystal poor, so hot. There's a big discussion, or crystal rich, so colder. Maybe there is 20 degrees only between these two. So that means we have storage of magma and storage of zircons, which is transient in space and time. We cannot model nor know when zircon is growing and where it comes from when we analyze them at the end. And we have to, so all this we have to understand, because now we go to the sediment, or to the ash beds in the sedimentary environment, and we find everything again there. So all this complexity we have now to have in mind when we start to interpret zircon dates in an ash bed. And now I will show a few examples, and all the examples I'm using are coming from the Permo-Triassic boundary, from southern China, so a Permo-Triassic boundary and lower Triassic. So this is a long standing collaboration with people at the University of Zurich, and there's coming from the southern Nanpanjiang Basin in southern China. So I stick to this for the sake of simplicity. So okay, now we are in the sedimentary environment. So we have our section here, which is straddling the Permo-Triassic boundary. We have here 4 ash layers, one, second one, the third one, the fourth one. They are quite ubiquitous in the field, are very well visible. So it's not always so easy that you see the ash beds. So we can actually, when we date these 4 ash beds, we can establish quite a good age model, and then compare this age model, correlate with biochronology, chemostratigraphy, whatever. Just don't forget that this is not a linear record of time. There's certainly major gaps, like here, probably like here, and there's also big changes in sedimentation rate, which we may not know, we may not see from the sedimentary record. And that's what we get, that's the same section. So we have, but now we're real data, so we have analyzed, I think there are 8 ash beds. So these diagrams here, so this is a single Zircon date, this is analytical uncertainty. This is a group of 4 analyses, and this is the weighted mean age of these 4 analyses at the 2 sigma uncertainty. So that means these 4 analyses are statistically equivalent. That's the case for DGP 21, 17, for this one, for this one, for this one, for this one. Very nice. So we have statistically significant clusters. We can take our weighted mean age as the age of the deposition of this ash bed. Of course, this is an oversimplification. The Zircon crystallized in the magma chamber, was flying through the atmosphere and being deposited. There is an unknown delta T between crystallization and deposition. And then you see here, we have another sample that's clearly too old. It's out of stratigraphic sequence. It's too old. So we can say, okay, it's out of stratigraphic sequence. This is Zircons. These are Zircons which crystallized earlier in the magmatic system. And then we have this problematic case here. So we should take the youngest cluster because it would date the sediment or approximate best the sedimentation, but it's too young. It's also, again, out of stratigraphic sequence. But if we did not have the stratigraphy, we would probably take this. And this is again too old. But this is all very subjective. You realize how much subjective assessment is in the interpretation of these high precision data. So how could we go away a bit, okay. So there's lots of subjective decision and assumption. So should we now take the youngest grain? We said that the youngest grain is the maximum age of the deposition. Should we now take only the youngest Zircons, or do we take the average? No, we have to take the average because this is a statistically significant population. And the scatter we have here is only analytical. So we are obliged to take the mean, the statistical mean. But we still subjectively exclude here a too young age, here a too old age. We have a very serious problem of undersampling. How big is the probability that we really have the youngest Zircons here? Probably 0. We have 10 million Zircons and we analyze 11. We can model this probabilistically. It's close to 0. We also assume that all these 11 analyses are distributed normally around the mean, which is certainly wrong, as I showed before. So we can improve this by doing some very complex Markov chain Monte Carlo bootstrapping Bayesian statistic approach. Doesn't really change too much when the data are so good as they are here. And importantly, we think we have to assume that we have propagated all our analytical uncertainty correctly. So all the rest is natural. There is no analytical excess scatter. This may also be an assumption which is not always true. So what can we do to get less subjective? It's the same section, same ash beds. And what we do now here, we calculate a model age. So we use our 1, 2, 3, 4, 5, 6 dated ash beds. There is one more, but it's dropped out. So the red ones. Now I have to quickly close the window. And now we apply. There are many different codes on the market, and some of you are very actively contributing to this. But the two mostly used, at least I can say the two which were used by my people in my group here are Bicron and Aberration, which have a bit different possibilities of putting prior assumptions into the equations. And now we can calculate through these dated red spots the best estimate of an age, of a age depth model. So This is the age depth model here, the line, and this is the associated uncertainty. And we see that, for instance, the DGP11, which was the problematic one here, this one drops out. So the model itself identifies this sample as problematic. And now we can actually use a model age, for instance, here of the Permo-Triassic boundary. We can calculate the model age here with its uncertainty. That's our model age for the PTB. For the PTB in this section. And now we can go in different sections. So in the Nanpan Basin, there many people have been working. So when we compare now at age models we have established in Dongpan, in Penglai Dan, this is platform, this is a bit platform slope. With the GSSP Meishan, we can calculate, so these are our data from Geneva, these are MIT data, Burgess et al. 2014, and these are again Geneva data. So we can compare, we arrive at solutions, model ages for the PTB in 3 independent sections, and we see that they are different, but they are coinciding within their analytical uncertainties. And now we have quite a bit of confidence. We can now start to correlate from these different sections. So we may have oxygen isotope curves, we may have carbon isotopes, rancium isotope curves, a lot of interest recently in mercury concentration curves, correlated to biochronology, or also correlated to astronomical solutions. So this is one way how we can correlate sedimentary sections via an age model. And we also tried other things. So we also managed to correlate ash beds in different sections via apatite. That's another mineral which is in ash beds. And by pure chance, we found out that in one ash bed, the apatite has a really, the composition, we determined the composition of the apatite, so magnesium, chlorine, iron, and fluorine concentrations, and has a very strange bimodal distribution. And then there is another ash bed where the apatite has the same, completely coinciding bimodal chemical composition. The 2 ash beds are exactly the same, so we could actually pool them together. So that's this ash bed is just before, at the very end of the Permian, just before the Permo-Triassic boundary. So this would be another way of correlating ash beds between different sections. Has not really been repeated so far. And now the last thing is, because we are interested in planetary processes. So we have on one hand now here one of the major extinction period in the evolution of Earth. And on the other hand, we have to think about what was triggering this. So we know it's a large igneous provinces. So we have a lot of greenhouse, icehouse gases, which are expelled in the atmosphere. So we need also to have a good chronology, a very good geochronology from the large igneous province we think is the trigger of this extinction here. So these, in the case of the Permo-Triassic boundaries, these are the Siberian traps. There's a very good geochronology done by the MIT lab, so Burgess and Bowring, 2015. So we can very easily show that there is a very good synchrony between the biotic events and the volcanism. But now is the question, can we now, are we capable at some moment to distinguish between coincidental synchrony, which also exists in our sciences, or in the development of Earth, coincidental synchrony or causality? So how do we get there? So this is a huge large igneous province. And this is the part of basalts which is kind of outcropping, lavas and tuffs, and this is the part which is subcropping. So there are thousands of drill cores. And these are 300 kilometers, so you can calculate how many how many millions of square kilometers this is. So all the intrusive part of this large igneous province, so dike sills, they cut through the sediments of the Tunguska Basin, full of organic matter, of coal seams, but also of evaporites. So we can imagine that massive amounts of CO2 and also SO2 were injected into the atmosphere and led to the climatic change, which we need to have so much impact on life. So finally, the causality we want to establish is basalt dikes as the trigger, and the reaction of life, the gas load in the atmosphere, and then the climate reaction as the effect. So this we get by dating of these rocks. This we get by dating ash beds in sedimentary successions, where we can establish proxies, time series of proxies, which gives us an answer about the temperature, about CO2 concentrations in the atmosphere, about biodiversity. So in the case of the Siberian traps, so Burgess et al., they claimed that, so it's very well dated, there are many very precise data. So there was first eruptive period or activity, and then they stopped, and then there is what they call the eruptive hiatus, where only intrusions, these dikes and sills which intrude into shales and sediments which are rich in organic material. And the onset of this eruption hiatus is coinciding with the extinction interval we can determine from the sedimentary sections. So is this now coincidence or is this causality? And now we want to go a step further. So because when we look now in the further development of the sedimentary record in the lower Triassic, we have something like, over these many years, we have something like 25 very well dated, very precisely dated ash beds spanning the Permo-Triassic boundary, latest Permian, Permo-Triassic boundary, up to the middle Triassic. We know very well these magic, the ages of these boundaries, early middle Triassic, Smithsonian, Spansian, Permo-Triassic. And we also have thousands, virtually thousands of carbon isotope analysis. So this is kind of a summary curve, a compilation of all available material from the Nanpanjang Basin. And when we now put our eruptive hiatus here, so this green period here, into this diagram, into this age model, we see that actually the Siberian traps, they stopped middle Tynerian. And actually there was the initial kick, which was definitely lethal for the marine life. But then the fluctuations of the carbon cycle were not so important, and then became very pronounced with fluctuations, changes of up to 8 per mil in the delta 13C. They are afterwards. So we come to the conclusion that this is the trigger of a extinction event, but these huge fluctuations of the carbon cycle, they have no volcanic origin. So now, of course, I don't want to go further now. We have to test, is this cyclic or not? And when it's cyclic, could it be related to Milankovitch or any other external mechanism? So we can come up with, via these age models, we can come up with global models of Earth atmosphere coupling, so global circulation models, which would explain the reaction of the carbon cycle. So this is kind of, this is the end product from the understanding, the dating of the Zircon to the so sophisticated models. So these are models we are trying to establish at the very moment with physicists of University of Geneva, so climate physicists. But now I want to go back to the interpretation, because we have one point left. What is natural variation and what is analytical variation in all this? We have to have an incredibly good control on our analytical parameters. So precision, we would like to have the optimal precision. So we're heading for something like 50,000 years, still a lot of time. That's the best we can kind of achieve at the Permo-Triassic boundary. We would like that we analyze this all the time in our lab. So whether we have data from 2019 or last year, we should always be measuring exactly the same. And we also should measure the age-certified reference materials to be sure that we are measuring accurately. So the age we are getting out is accurate relative to a certified material. And also other labs should measure the same. Princeton University, MIT should measure exactly the same. So there are several aspects to this. This is called repeatability. This is called reproducibility. And the reality is not always so bright. So this is a compilation of a synthetic solution we are measuring over long periods of time, 2008 to today. And you see that this is an outlier. The nominal age is something like 100.15 million years. And you see there are huge fluctuations, up again, down, up. And we have only realized in 2018, end of the year, that there is a problem with spike samples, so equilibration in the lab. So equilibration between two aqueous solutions in the lab is a problem. We were not aware of this really, and since we are aware and we have modified our procedure, we are reproducing this value within about the tenth of a per mil. And we also can intercalibrate different mass spectrometers at this best precision, not only in Geneva, but also with Princeton University, with ETH Zurich, that's shown here. So this is published very recently published in the Journal of Analytical and Atomic Spectrometry. So we are confident now, labs who are within this Earth-Time Consortium, that we do manage to repeat and reproduce our uranium lead dates within a tenth of a per mil of uncertainty. So we have constantly modified our techniques, and this has one big drawback. And this is, I think, this is the difference for you non-geochronologists to understand, to get this. So the dates which were produced pre-2008 cannot be really anymore directly compared to dates which were produced afterwards. A good example is one of these ash beds in China. So 2007, the red analysis gave this age, 251.2. 2020, the same ash bed, of course, other zircons, but same petri dish, same sample gave this age here. Many things changed in these 13 years. So many measuring conditions changed, new generation of electron multipliers. We had our Earth time spike with a very precise Earth time spike calibration. We changed actually the isotope composition of natural uranium. Uranium we measure as an oxide. We have to introduce an oxide, oxygen isotope correction in the measurement. This was at the very beginning of chemical abrasion. And this was now, we are confident with chemical abrasion. So what we did in 2007, we were not sure about the chemical abrasion. We took the oldest analysis and we thought the younger ones, they have still lead loss. And now we are confident with our chemical abrasion. We take the youngest analysis and consider the others as pre-depositional growth. And you see the difference is significant. And we cannot go back. We are constantly asked, can we go back and correct for this? No, we cannot. There are too many parameters which have changed. We can only reanalyze it. Okay, so we as a community, we are quite confident that we can secure a CAID TIM state at this level of precision. Now I put the 2. Now I could also put the 1, but I think it's more realistic a 2. The repeatability is still to be improved, and I mean, next month or 2 months we'll get an upgrade of one of our mass specs here with new technology. I think this is not finishing. This trying to get to better repeatability and better precision. This will not so much influence the precision, but the repeatability. It's constant mass development, which is a problem to understand for outsiders. But now we are at the precision where we can start to think, to dream about assessing causality between planetary processes. But of course, this is going via models. This is not just showing it's the same age is not enough. I mean, coincidence exists. And still 50 years of uranium lead dating, we are still struggling with the initial and biggest problem of the radioactive decay damage of zircon. And do not forget, this is very important for people who are outside the field. There are these 3 methods. The cheapest one is laser ablation Icpms. So let's do this. We can analyze 20 samples. You cannot, a given technique cannot resolve a geological process which is shorter than the precision of the method. You cannot, with a method which is producing 2% uncertainty, you can resolve a timing which would be in the per mil of uncertainty. So CA Icpms forever. So that's why we are called by the others the CA Icpms snobs. And that's it. Thank you very much.
Thanks a lot for this very broad view, and thanks for starting very gently for us who are not specialists at all in this field. I appreciate the effort of the beginning as well. So yes, we can have plenty of questions now, and Linda has a question for you.
Well, thank you for a fantastic talk, Urs. So I saw I wasn't surprised, but I saw that now you are proposing to ignore the lead-206 uranium 238 ages.
No, the 207, 235.
Oh, I'm sorry. Yes. Yeah. 237.
Yep.
Yeah. Sorry. 207, 235. I'm sorry. Yes. But when you do that, then you lose the ability to assess the closedness of the system. And so do you think that's worth it, or do you collect everything anyway and then go to that analysis when needed? So for example, I noticed that you had some 206, 238 ages with a lot of spread in them.
Yep.
And you said, well, you know, we can only statistically use these, but maybe you could assess whether or not they're discordant, or that's gone now.
Yeah. No, of course we measure. First of all, we measure, of course, all. This is completely clear. But as you see here, discordance can only be produced by changing the isotope composition of our common lead. So actually, the value of discordance has completely degraded. But of course, we do analyze both isotopic system. But usually, we have when we plot our data, they are here. They are maybe in a small box here. So you can have your 1% of lead loss, and they are still analytically all concordant. So the discordancy argument only starts to hold when you have larger percentages of lead loss. So this, of course, we want to avoid, because we want to do our chemical abrasion as well as possible. So when I want to draw, so I mean, I can go to an example. I didn't prepare now a Concordia plot, but these are all perfectly concordant points, and even those I kicked out. These here are all perfectly concordant points. They're just scattering in age. They're scattering along the Concordia. So this is degrading the discordance.
How will you, let's ask another question, a related question then. How will we ever know whether or not there was truly lead loss versus you know, the actual age? Trace elements? I mean,
no, I think we have tried everything. I think that the most interesting is to use Raman spectroscopy. So imagine you would go with every zircon before you analyze it. You would go on a Raman spectrometer, establish where you can do mapping. You can establish a map. Then you go to do chemical abrasion. You come back, you do the mapping again. This would be an enormous amount of work to find out finally that we have decreased our damaged volume of the zircon from 60% to 7%, for instance. This would be feasible, but I think it's not feasible in terms of a workflow.
Right.
You know?
Right.
It's not only about quality, it's also about quantity, because we want to have dates from a certain number of grains in one sample. We want to have a certain number of samples from one section. So it's kind of a trade-off. And even with this, we have now defined this highest confidence area, but we still have damage there. It's clear we never get here, we are here.
Yeah. Nonetheless, the advancement has been spectacular for the methods.
Yes.
Thank you.
Welcome.
Paul?
That answered actually my first question, although I guess for some, especially when we're dealing with detrital zircons, it would still be really nice to be able to do the Raman on the after chemical abrasion to know if there are some crystals that are going to be outliers. But I think you answered that question. I have another question. I assume then in your different ashes in the sections in China that your boundary age is actually coming from the same ash that's spread over a very large area. Is that correct? That's what your appetite argument was saying?
Okay, so where is the appetites? The appetites were here. So the appetites, these were two samples, one from the Beng Dun section. Where is this? This is not here, right? And the other from the Wusuan section.
Yeah.
And so actually these age models here, they are from other sections. So that's Beng Dun. This is a bad model. It's not covering too much sedimentation, so too many meters. And actually there is other data from Jahan which are disagreeing with these, and these are too old. So this is another aspect. So Jahan, his age model goes down straight here. He doesn't.
I didn't quite mean that. I meant the individual ashes that are dated at each of those sections that are shown in the yellow box.
Nope.
Is that physically the same ash at different localities?
No. This is the model age.
Okay.
Model age.
Aren't there criteria for helping you to recognize the same physical ash?
Well, this is what we try to do with the appetite chemistry. Right. Yeah, I think this could be a way to go. It's just a lot of additional work, but this could be a way to go. So instead of dating all these ashes, you can date maybe 1, 2, and you realize, okay, this may be the same ash in different places.
Right.
And you could use appetite chemistry, which only needs a microprobe, but not a sophisticated lab.
So then my last question is, it looked to me on your time diagram that had the various Siberian trap events and your ages, that what actually was coincident, at least temporally possible, as a cause of the event were the pyroclastic eruptions and the composite lava section, right? Not the intrusive magnetism. That happens after.
So this green window, what he called the eruption hiatus, this is this green box.
Right.
So we have before pyroclastic.
Yeah.
We know that the biotic response starts before the Perma-Triassic boundary, so we do have volcanic activity here.
Well, I would be very cautious about that statement. That statement is a statement about statistics.
Yeah.
You say the biological thing starts before the event. That's a statistical statement, which I don't think is necessarily supportable. So you're telling us that some conodont expert has told you that the conodonts are disappearing before the event. Well, you know, conodonts are discrete. And
yes, and you have, of course, you have to do statistics to distinguish between the background extinction and then the pulsed extinction, which has an external trigger. Yes.
And the environment is also statistical. So when the conodont animals can be around, or whoever it is, the environment itself is fluctuating. So you have the sampling issues of the organisms, and then you have the environment, which is switching in and out. And so those are not really separable. So I'm always very cautious about the biological statement. But going back to the possibility of causation, which you had in that previous diagram, where in which you show the pyroclastics and the lava flows, that one, it looks to me like the only possible causal mechanism there are the composite 4-kilometer lava strat section, 2/3 of erupted total volume. That occurs at the right time for causation. Not
so this would precede the extinction interval or the extinction.
Right.
Yeah.
And so that occurs, it makes it possible for that to be the event rather than the intrusions.
Well, that's one aspect, just purely argumenting purely temporally, yes. But the argument is another one. You know, the argument is that the intrusions are the contact metamorphism of these sediments, which host
the self argument.
yeah, but they also have feeder dikes which cross-cut these sediments. So
right, but the heat input of the feeder dikes has got to be minute compared to those sills and intrusions. So I would argue that this diagram is a very strong case for the outgassing of the lavas themselves to be the origin of the events. Of the event that caused the extinction, and that this argues strongly that the intrusion had very little to do with it.
So what Philip was trying during his thesis is exactly this. He was trying to make a very simple box model, so CO2 volumes, and I think it's too primitive to really say, because there were no physicists involved, climate scientists involved. But he came to the conclusion that the CO2, the volumes of CO2 which are stored in the magmas are by far not sufficient to produce this. You have to have a very big, an important contribution of the sediments.
Maybe it's not the CO2. Maybe it's the sulfur, and the sulfur is coming out in the initial pulse of the lavas.
Yeah. So I mean, we are, since on the basis of our work, we have always kind of claimed that there is a very short cooling event here, which is a kind of the Zurich-Bucher specialty. And this will be coinciding with the sulfur, with the SO2. Yeah.
Thank you. Yeah. Great talk. Enjoyed it.
Any other question? I have one.
Mm-hmm.
I have several, but I start with one. You show some very impressive 0.02% time determination, but and then you say that several laboratories find the same. My question is, what is the account of the decay constant uncertainty in this? Do you all use the same decay constant? And what is the real uncertainty of the decay constant, and how? What is its contribution?
So that's a very important issue. So these are all labs which are in the EarthTime consortium. So we are all using the same tracer solutions. That gives us the possibility to compare our results with analytical uncertainty only. So no external systematic uncertainty, only the random analytical uncertainty of our procedure in our lab. So this would add, if we had now different tracer solutions in these different labs, this would add maybe another 50% to this uncertainty here. And when you want to add then the decay constant uncertainty, then this would double the uncertainty again. So when you compare uranium lead dates, very precise uranium lead dates with argon dates, you should add the uranium decay constant uncertainty, because argon dates are produced with another decay system. But
how much is the uncertainty on the decay constant? How is it?
I can really not tell you by heart. The only thing is, it is quite big. It's propagated when you choose this in the calculation. It's so the uncertainty is fully propagated into the end result. And but the uncertainties was Jaffe et al. is one publication. The uncertainties are only estimated. There was no statistical treatment of data at that time. So we are basing actually our whole analytics. We are basing on decay constants which are determined so long ago, and the uncertainty of these determinations is estimated. That's of course to be fixed. This is a big problem. Yeah.
Okay, so you are basically showing that using your technique, you find a very accurate result. You find when different labs find the same results with very good uncertainty, but you may have a bias that comes from the assumption done on the decay constant or on that. So indeed, yes, that's.
But of course, we are all using the same. There's only one decay constant in the literature. At least this, we are using the same.
Okay.
And we're also assuming that the duration of a year is the same as it is today.
That's a good assumption. That's a good assumption because in fact, the semi-major axis of the planets don't change in average, or practically don't change. They change because of the mass loss of the sun, but that's very mild. So, but still, maybe it should be taken into account in because that could be an effect. And okay, that's interesting. So it should be nice to put all these errors in perspective, to have an idea of what is the real, because what we want to know is what is the real uncertainty at the end. That's I have another question. Yes, you had another comment on that? I had another question about chemical abrasion. I may not have totally understood exactly what it is, but you show a picture at the beginning showing parts of the zircon which are well ordered, that have not been yes, this picture. You show this picture. You show that in fact what you want to get is the part of the zircon which has not been destroyed by the decay, by the ejection of particles. That if I understand well, is it? Why is it possible to just take I suppose it's an electronic microscope, and to just pick up the place which is pristine in the zircon? Is it possible? Would it be possible? Is it too small?
Well, we would have to have a device which is cutting out these areas of zircons which are pristine.
Yes.
So this could be, you know, this could be a very, very thin laser beam, or this could be one of these, how it's called, FIBs, ion cutters. So, I mean, we can analyze really small areas. The problem is more how to handle them, because they're still pieces. So we have, this is one of my projects. I failed miserably in my career. I wanted to develop a robotic system to do this with laser and micro robots to handle, because this you cannot handle anymore with your hands. So, but it was not funded. Yes, this would be possible. Yeah? But ideally, what the world needs is that we have something like an ion probe, which is measuring at this precision. So we have to develop a machine which has a very bright primary ion source, which is ionizing a lot of material here, much more than now, and so it gets rid of all these different interferences on the way, and has a very, very sensitive collector unit at the end that we can measure this few little material at the precision we measure this. And this, I don't know whether this is physically possible, but when I see how the ion probes are working today, there is plenty of room to improve present-day ion probe technology. And maybe in 50 years, this will be possible. Then we are out of this problem. Then we can go and do maybe some TM or whatever imaging, and say, okay, this is nanometers, of course. If this now was micrometers, okay, this is an area we can analyze. This would be optimal, yes.
Okay, so I understand. There is some perspective for some progress. That's good.
Yeah, I don't know whether this is realistic physically. This I cannot judge, yeah, but there is, yes.
I had another question, in fact, which is on the maybe slide 27 or something like that. All these, yes, or maybe the next one then, maybe. Yes, all these. So if I understand well, each measure that is here is made at a different place of the zircon, and they correspond to different age because of the growth of the zircon. But
no. These are, each one of these is one single grain of zircon.
Is
one single grain of zircon. Each one is one crystal.
Oh.
We cannot analyze different, of course we can break it into 2 or into 3 fragments. This we can do, but we cannot analyze, this is exactly the point. We have no instrument which can analyze different points on one zircon. So these are single crystals.
Okay.
Yep.
You cannot discriminate you cannot take something on one level. You had a picture maybe I don't know.
Yeah, I know what you mean. I have to see what this is. You mean this one here?
Yes.
Yes. So this would be ideal, of course. We have an ion probe or something like this where we can analyze these 4 zones separately.
Yes, that was my question. Yeah, so I didn't understood everything, but so this is not possible right now.
No.
Okay.
We can only analyze 4 grains. Grain 1, which may have mainly the zone 1, or the grain 2, which has mainly only formed during this period 2, or grain 3 or grain 4. So the duration of growth we see here from single zircon is a minimal estimate of the real duration of growth, because each of these zircon analyses here is already an analysis of such a zircon, which has different growth zones.
And but could you make you have different growth zone, but you can think that the size of the zone 3 is bigger than the size of the zone 1. So
yes,
the probability to be in 3 is larger than to be in 1. Do you take this kind of thing into account?
Yes. So what we can do is we mount our zircons in a resin, and we do imaging. This is cathodoluminescence imaging. And so we can then come up with kind of a sequence of growth events. And then we see that one zircon has mainly, so the volume, we can calculate the volumes, has mainly volume 3, another zircon contains mainly the volume 2. And then we take them out of the epoxy and analyze them. So we can make a relationship between what we see in the CL image here and the date we produce from this grain. But the date will always be a mixture of these growth zones.
Okay. Okay, thanks. That's all for now. Are there any other questions? Matthias?
I had a question, a conceptual question, Urs. We don't have bentonites everywhere, right? Unfortunately. So some people start just dissolving a bunch of limestone or something, and then what they think are volcanic zircons, date them, and then put them in their H model. Do you think that's a valid approach?
Yeah, well, you do whatever you can when you don't have ash beds. Huh? So this is not the worst you can do.
Okay.
When they are zircons in carbonates, then and they have kind of a morphology which is volcanic, yeah, why not? But then you can try to do carbonate uranium-like dating, which is then comparably very, very imprecise. But we also try now here. We have kind of also in this area we have kind of a good development at the moment, because the people are doing this only by laser. So because we have to have many points, so we are going one step further, and it's quite interesting. So I think you know, there is potential in many places to improve the things. And for instance, in the Neoproterozoic, we obviously do not have ash beds, so we have now fantastic drill cores in many places, and there is the people are analyzing the same ash bed again and again and again. So there is a need to develop other approaches, or rhenium osmium dating of black shells, that you can get to a H model. And the H model should be capable of handling high precision dates and low precision dates also. So it's quite a bit of of modeling behind.
So related to the age modeling for the Bayesian age step models, for now, at least as far as I saw, you don't really take the sediments into account. It's almost linear between different dates. So if you have 10 meters of limestone or shales, you don't really differentiate. Or if you have different phases, do you think there would be important room?
Okay, so that means that you put an additional prior, which is taking into account the sedimentation rate. That is I wanted to do with one of my last PhD students, but I had to stop the thesis, unfortunately. Yeah, this would be exactly the way to go. Yes. So
yeah, we're also
adding more priors into the model. Yeah.
Yeah. Okay, I agree.
Yeah.
So if there are no other questions, I should thank you again because you fully answered to my to my request and giving both a very slow beginning, which was very good, at least for me, because I didn't even know that there were so many stages going from uranium to lead. I didn't, so that there were all so many intermediary stage before going. And is there any interest of measuring them? Will it improve anything?
So not for what we are doing, but you know, this is what is called U-series dating. You can take, for instance, 240, 234 uranium and 230 thorium only in carbonates, and here you are at the decay, at the half-life of 75,000 years. So you can actually date marine carbonates with this. So there is an interest, just for forgetting about what happened before to some extent, and forgetting what happens afterwards, and using this as a decay system. Yeah? This is a completely U-series dating, is another world. We don't speak to each other. So, but there's a lot of interest, yes. Also with radium, and then in environmental sciences with, where is it? 2010 lead, because the 222 radon is a gas, goes in the atmosphere, is happily continuing to decay, and then it comes down on the surface of the Earth as 2010 lead because it's raining out. So you can start your calculation from 210 lead, isolated 210 lead. So there's a lot of applications. Yes, environmental sciences, volcanism, paleoclimatology of the last 300,000 years. This is a huge field.
Okay, thanks. So if there are no more questions, I don't see any hand that is raised. I think we can thank you again.
Was a pleasure. Thank you. It was a pleasure also to see some of you. And I know I started as a magmatic geochemist. And the fact that I know actually nearly most of you shows also that I kind of completely shifted over to sedimentary research, which is nice.